Welcome to the tutorial on properties of Laplace transform. So in this tutorial we'll be discussing about different properties of Laplace transform. So I'll start with the first property, that is linearity property. Linearity property, right? It's pretty simple. We already know the relationship between the time domain signal f of t and its Laplace transform, that is f of s, right? So I can write this as Laplace transform here. So if f of t is a time domain signal, f of s is its Laplace transform in s domain. Now here, if you notice, you have a single signal f of t whose Laplace transform is f of s. Now what if you have sum of more than one signal, right? So let me take signals as f1 of t plus f2 of t plus f3 of t and so on, right, till fn of t, right? If input is a sum of time domain functions like f1 of t, f2 of t, f3 of t till fn of t, then the Laplace transform of the sum would be the sum of Laplace transform of individual time domain signals like f1 of s, because f of t's Laplace transform is f of s, f1 of t's Laplace transform is f1 of s plus f2 of s plus f3 of s till fn of s. So this is the property of linearity. Now, how do we prove this? Let me take the left hand side, that is this entire term, that is sum of time domain signals, and I will be taking Laplace transform of them. f1 of t plus f2 of t plus f3 of t and so on till fn of t. Now, from the basics of Laplace transform, we know that Laplace transform of any function f of t, Laplace transform of f of t is given by unilateral Laplace transform 0 to infinity f of t e power minus st dt. Now in place of f of t, if f of t was there, I would be writing f of t here. So we have sum of these functions, right? So my equation, Laplace transform equation, will be 0 to infinity f1 of t plus f2 of t till fn of t into e power minus st dt. As simple as that. Now if I take e power minus st dt term inside the bracket and split the integral, I will be getting 0 to infinity f1 of t e power minus st dt. This entire term I have taken it and multiplied with f1 of t. Then you have plus term plus f integral 0 to infinity. It is a sum of integrals, so I can take the integrals to individual terms. So it is f2 of t e power minus st dt. Similarly, it will carry over till the nth term, 0 to infinity f1 of t e power minus st dt. Now, from the basics, Laplace transform of f of t is integral 0 to infinity f of t e power minus st dt. That is nothing but f of s. So similarly, I can write this as f1 of s, second term as f2 of s, and till the nth term as fn of s. So this is my right hand side. So I have started from the left hand side. I have taken the Laplace transform. I have indicated by L, and I have proved it to be equal to the right hand side. Now the second property which I will be discussing is complex translation. Complex translation, right? So what does it say? If we already know f of t, a time domain signal, forms Laplace transform pair with f of s. Now, if there is a multiplying factor e power at f of t, that means you are multiplying with an exponential. You are multiplying with an exponential to f of t. What is the Laplace transform? It is given by f of s minus a. Okay, where a is the complex quantity. So if you multiply an exponential with the time domain signal, you would be getting a shift in the frequency domain signal. I mean s domain signal, not frequency domain. It is s domain signal. It was, if it was f of t, you would be getting f of s. If it is e power at f of t, you would be getting f of s minus a. So how would we prove this? Again, as usual, let me take the left hand side and take the Laplace transform of it. So Laplace transform of e power at f of t, which is nothing but integral 0 to infinity. In place of f of t, you have this term, so e power at f of t e power minus st dt. Now I'll get f of t out. I'll combine these two terms together, e power at and e power minus st. I'll take minus out, so I'll be getting e power e power minus s minus a into t dt, because s is here, a is here, and t is also there. So you will be getting s minus a, minus into minus, it will be plus a, so e power at you will be getting. Now from the basics we have, what is the Laplace transform of f of t defined as, which is nothing but f of s. It is unilateral Laplace transform. It is f of t e power minus st dt. Now, see, Laplace transform of f of t is defined to be f of s, right? F of s, and that s came from this integral, wherein exponential is raised to the power minus s. So if you have s here, you would be getting f of s. But in this integral, you have s minus a, so this would be f of s minus a, right? So this is the proof for complex translation. Now extension of this is, if what if you find and this is equal to the right hand side, so we have proved. So the extension of this is, what if you have a negative sign on the exponential, e power minus at f of t, right? This would be f of s plus a, so there will be only a sign change. This can be proved on the same lines by I'm substituting e power minus at here. So if you take minus out, you will get s, and since you already have a minus sign here, so you get s plus a, so it will be f of s plus a. Now this would be useful in solving if you're problems like this. If you are given with a problem wherein you have to find Laplace transform of e power 2t sine of 3t, right? So this is of the form Laplace transform of e power at, right? E power at f of t. And for this, what is the Laplace transform? We have already found f of s minus a, wherein what is f of s? F of s is Laplace transform of f of t. What is f of t here? It is sine 3t, and its Laplace transform of, sine 3t is Laplace transform. I'll be writing that here. Understand, this is pretty simple. See, Laplace transform e power at f of t is f of s minus a, wherein f of s is Laplace transform of f of t, and f of t in our case is sine 3t. So if sine 3t is my f of t, what is its Laplace transform? That is f of s. If this is my f of t, what is f of s? It is omega divided by s square plus omega square. Okay, this I have proved in my previous videos, you can have a look into it. So this is omega is what? 3 is omega, so it will be 3 divided by s square plus omega square, 3 square, it is 9, right? So this is f of s. But from the property it says that if you multiply an exponential to f of t, it will be a subtraction in s domain of its Laplace transform, right? So what is the Laplace transform of f of t? F of s, that is 3 divided by s square plus 9. And if you multiply with e power 2t sine 3t, it would be replacing s by s minus 2. So 3 divided by s minus 2 square plus 9. So this property comes in handy when you have multiplication by an exponential to a time domain function. Okay, so the thing to be noted here is f of s is the Laplace transform of f of t, not the entire term. So Laplace transform of f of t is f of s. When you're given with an exponential multiplied by the function, take the Laplace transform of that function and replace s by s minus exponential raised to the term. See here, exponential raise is raised to 2, so it will be s minus 2. If it is exponentially is raised to minus 2, it will be s plus 2, and that is how we solve the problems under when a time domain function is multiplied with exponential function. So the next property which we are discussing is differentiation in time domain. In time domain. Okay, as the name says, we know that time domain signal f of t forms its Laplace transform pair with f of s. Now, differentiation with respect to t is differentiation in time domain of f of t would be, this is given by s into f of s into f of s minus f of 0 minus. Okay, now we are not familiar with what is f of 0 minus. Say f of t is a function in time domain and its value at t is equal to 0 is f of 0, right? So if you take an instant just before 0, it is called 0 minus. So the value of f of t at at t is equal to 0 minus is f of 0 minus, or you can consider it as a initial value. Okay, now how do I prove this? I will be taking left hand side, right, and I'll take, so left hand side is d by dt of f of t, right? So I will take d by dt of f of t as f dash of t. I hope everyone is familiar with the notation. It is the first differential of f of t. It is d by dt of f of t. Now I need to take the Laplace transform. It is 0 minus to infinity f dash of t e power minus st dt. You are multiplying your function, time domain function, with e power minus st dt. Now why you have taken 0 minus into consideration? See, there is a function called impulse function which exists, sorry, delta function or impulse function which exists only at t is equal to 0, right? Okay, so while taking unilateral Laplace transform into consideration, the lower limit of the integration is 0 to infinity, I mean 0, and the upper limit is infinity. So to take care of impulse function, we take 0 minus, because impulse function is a sudden rise at t is equal to 0. So we have to take an instant just before t is equal to 0. That is why we take 0 minus into consideration in this property. Okay, 0 minus is the instant just before t is equal to 0. This is again used to take care of impulse function while calculating the Laplace transform. Okay, impulse function is delta of t, which I've discussed in my signals and systems video. So if you have doubt, you can go through it. Now this is integration by parts, right? So you have multiplication of two time domain functions, f of t, f dash of t, and e power minus st. So it is, I'll take this as the first function, this as the second function. So it is first function, product rule or UV rule, first function, that is e power minus st, right, into integration of second function is f dash of t dt minus integration of differentiation of the first term. Remember, we have to differentiate this with respect to t. So s becomes a constant. So it is e power minus st into minus s, because you are differentiating e power minus st with respect to t into, this is different, see, first function into integration of second minus integration of differentiation of the first term into integration of the second. Integration of the second is f dash of t dt. This is integration of this, and for this integration again you'll have dt, right? Now if I can take this into the bracket to make it very clear. So here I would be having e power minus st. I have taken it out. I mean, as per UV rule, what is the integration of f of t with respect to f dash of t with respect to t? See, integration and differentiation are inverse operations, so they get cancelled out. Cancelled as in, say, integration of differentiation of f of t is f of t with respect to t is f of t. So this integration and differentiation, f dash is differentiation, so they get cancelled. I'll be getting f of t with from 0 minus to infinity, and here minus and minus s and this minus, so I'll be getting plus term s into integration of 0 minus to infinity. See, what is again integration of differentiation of f dash of t with respect to t? It is f of t. So I'll be getting f of t e power minus st dt. Right? Now, if I apply the limit here, if I apply the lower limit, e power, remember this limit is on t. So t, if I substitute it here, it will be 1, and I will be getting f of, sorry, I need to apply the upper limit first. So infinity, if I apply e power minus infinity, it will be 0. Doesn't matter about f of, don't worry about f of infinity, because since one function is 0, 0 into something is 0. So I'll be getting 0 minus, this is, if I put 0 minus e power 0 is 1, so I get f of 0 minus, this is plus s into, what is this function as a whole? Integration 0 minus to infinity, f of t e power minus st dt. It is nothing but f of s, that is Laplace transform of f of t. So the term what I get here is s into f of s minus f of 0 minus, where s is the Laplace domain signal, I mean symbol. F of s is the Laplace transform of f of t, and f of 0 minus is the initial value of f of t just before the instant t is equal to 0. Now this can be, this is Laplace transform of df of t by dt. This is first differential. First differential. Now this can be extended for second differential or third order differential, a differential of f of t. So Laplace transform of d square f of t by dt square would be s square into f of s minus s into f of 0 minus minus f dash of 0 minus. Okay. See, here the order was 1, first order. So you'll get s to the s raised to the power 1 into Laplace transform of f of t, that is f of s minus its initial value. Here if you have order 2, I mean degree 2, sorry, order, it is order 2, so you get s square into f of s, because here the order is 2, so s square into Laplace transform of f of t f of s minus 1 less than this order, that I mean 2, it is s into f of 0 minus, that is initial value, minus f dash of 0 minus. On similar lines, you'll get Laplace transform of d cube f of t by dt cube, right? So nth order derivative, here order is 3, so you will be getting s cube because the order is 3 here, s cube into f of s minus 1 less than the order s square into f of 0 minus s into f of 0 minus f dash of minus f double dash of 0 minus, right? So I guess you can predict this. See, the s term will go on reducing, s square, s and s power 0. Here also s cube, s square, s power 1 and s power 0. Only thing is first term will have Laplace transform term and remaining will be the initial condition one. So this is the generalized Laplace transform for nth order differential of time domain signal f of t. So if you have first order, it is s into f of s minus f of 0 minus. Second order, s square into f of s minus s into f of 0 minus f dash of 0 minus. Third order is the equation which I've shown here. Right. Now the next property number 4, if I may call it. So it is multiplication by time domain function, right? Multiplication by time domain function, or I can simply write multiplication by time domain function, which is t. Okay, multiplication by t. Now to start with, we know that f of t forms a Laplace transform pair with f of s, right? Now this property says that the Laplace transform of t into f of t forms a Laplace transform pair with minus d by ds of f of s. Okay, minus d by d, if I were to change this, d by ds of f of s. So in the previous property, we have checked that the Laplace transform of differential is s into f of s minus f of 0 minus, whereas if you multiply the time domain function with the time domain function t, its Laplace transform is differential of the Laplace transform of the time domain function. Now how do we prove this? Now let me take the simple Laplace transform equation f of s. What is it? It is 0 to infinity f of t e power minus st dt, right? Now let me differentiate both sides right by, with, I mean, not by, we say with respect to a variable. I'll differentiate with respect to s. Okay, I'll differentiate both the sides with respect to s. So I'll be getting df of s divided by ds, okay, equal to, see, this is integration with respect to dt. If at all you had an integration with respect to s, then if you differentiate and integrate with respect to s, they would get cancelled. But now here the integration is with respect to the variable t and we are differentiating with respect to s, so that is why integration and differentiation would never get cancelled. So this is the doubt most of the students will have, including me when I was a student. So since the integration is with respect to t, if you differentiate this with respect to s, the integration and differentiation will never get cancelled. Whereas when you differentiate with respect to s, s is looking out for only the s terms, not the t terms. So the t terms will become constant. So I can take this out, 0 to infinity f of t dt also I can take it out. What is the differentiation of e power minus st with respect to s? It is e power minus st into minus t. Remember why minus t? Because we are differentiating with respect to s. So this would be equal to, I'll take the minus term to the left side, minus df of s divided by ds. Here I will be getting 0 to infinity t into f of t e power minus st dt, right? So this is a t which I've written it here. F of t is this one, minus I've taken to the other side, and e power minus st dt. See, Laplace transform of f of t is f of s, which will write it as 0 to infinity f of t e power minus st dt. Now, since s is here, I will be writing capital F of s. Since f of t is here, we will be writing we will be writing this equation as Laplace transform of f of t. So similarly, here f of t is replaced by what? T into f of t. So this would be Laplace transform of t into f of t, which is nothing but minus df of s divided by ds. So this is the third property. That means if you multiply your time domain function, that is f of t, with a function, I mean again time domain function t, which is called a ramp function. I hope all of you are clear with the ramp function. See, t is a function with respect to t. That means f of t is equal to t. Here f of t, not f of t. F of t I have already taken, right? So I can take another function g of t as t. This t is g of t. This is f of t. So g of t is t. With respect to t, how do you plot it? At t is equal to 1, g of t, its value is t. Again, it is equal to 1. So 1 and 1 coinciding point is this. At 2, this value is also 2. So 2 and 2, the coinciding point is this. Similarly, you will get a straight line. So that is why it is called a ramp, right? So if you multiply a ramp to a time domain function, its Laplace transform is minus d f of s divided by ds.